Okay, welcome to our video we have here on logarithms. Really just everything to do with logarithms and integrals. So before we actually get into the problems, and this video is more of a review, I would say. Nothing new is going to come from this other than we're just kind of focusing on the logarithmic problems that we're going to have. Actually, there's some derivative problems as well. So it's just kind of a mixture of everything using logs. Let's go over some properties of log. This is all should be a review for you. So the domain of ln of x is from 0 to positive infinity. Here's the deal. Here's what a logarithm looks like. There's the axes. So the actual graph itself, ln of x, looks like this. All right, so this is what the graph looks like. It's very slowly increasing. Our domain's from 0 out to infinity. As you approach 0 from the right, we're going down to negative infinity. As you approach infinity, it's going to go to infinity. Our range actually covers everything. The graph is continuous and increasing in 1 to 1, which means it has an inverse. And then it's concave down. You just look at it. It's concave down. But here's kind of the interesting part. Never talked about why ln's have the properties that they do, and it's actually from this right here. ln of x is defined as the integral from 0 to x of 1 over t dt. This is the actual definition of it. So when you take the derivative of ln of x, taking the derivative of that's why you get 1 over x. And because of that, all of these properties are in play because of this right here. Okay, so you already know these properties. We're always just told that, hey, these are the properties, deal with it. Well, from this definition, this is why these properties work. And then we'll kind of play more into these properties as we go through the lesson here. So just some real quick things about ln of e is 1. ln of e to the x is just x. Because of that property, you can bring the x out in front. And this is just rewriting. And then, again, this is just change of base. This is all stuff that you should have known already from Algebra 2. Not even pre-calculus, from Algebra 2. And then here's some limit stuff that we have talked about in the past a little bit. But now we actually know how to find this by using LHOP. And we will tackle one of these problems moving forward. So let's quickly get to some problems with logs. All right, so find the derivative of this. Because it really doesn't have anything to do with logs, other than we're taking the derivative of a integral here. So this is going to be one of those chain rule things. So we got to plug in that sine of x into there. So it's going to be 1 minus sine squared of x times the derivative of sine of x. So this is going to be 1 minus sine squared of x, not touching that, times the derivative of sine of x, because again, this is chain rule. Take the derivative of your bound there and then plug it in. The derivative of sine is going to be cosine. Well, 1 minus sine squared turns into cosine squared. So we're going to get cosine squared x times cosine x, which is just cosine cubed x. All right, so nothing new there, just really review. Let's go ahead and find the limit as x approaches infinity of 1 plus 1 over 2x, all to the x power. So again, this is going to be one of those review problems. This is an LHOP. This is a LHOP problem. Remember how I said there's 3 LHOP problems? There's the ones where you just get 0 over 0 or infinity over infinity. You just need to take the derivative of it, and then you're golden. There's the phase 2 of LHOP where you need to rewrite it so they can get 0 over 0. And then phase 3 is when you need to use the ln properties. This is one of those because we have a variable in the exponent. So we can't just plug in the infinity because we're going to get 1 to the infinity if we were to plug this in. So we need to set this equal to y. Okay, so we're going to do, so this is equal to y. We're going to ln both sides. So if you don't mind, I'll put the y over here, just more familiar with that. We're going to do the limit x approaches infinity of ln of 1 plus 1 over 2x to the x. And this is where we just throw that out in front using our power rule property here for logs. So we're going to get the x out in front. if I were to plug in an infinity here, I would get infinity times infinity. So this is now turned into a phase 2 problem. So I need to rewrite this so that I can get a 0 over 0. So I'm going to change this as this x is going to turn into 1 over x on the bottom. Okay. So if I were to go ahead and check this, I should get a 0 over 0. And, well, make sure you formally go through this. I know a lot of you like whatever, I'm going to do how I want to do it. Well, you actually need to show this correct way. You will lose points if you don't. So if you plug in an infinity, you're going to get ln of 1, which is 0. You do need to show this work for LHOP every single time. 1 over x. You plug in an infinity, you're going to get 0. So you will get a 0 over 0. So you will have to LHOP this side of it. So we're still going to get ln of y equals, when you LHOP it, you're going to get the limit x approaches infinity of the derivative of the top here. It's just going to be 1 over 1 plus 1 over 2x times the derivative of the inside, which would be 0 plus negative 1/2 x to the negative 2, it looks like. I'm just double checking myself here. Yeah. So 1/2 should be negative 1/2. So times negative 1/2 x to the negative 2. So that's the derivative of the inside there. Derivative of the outside is the 1 over 1 plus 1 over 2x. Derivative of the inside is 0 plus, that's really an x to the negative 1 times 1/2. So that's why it's negative 1/2 x to the negative 2. And then this is derivative of the bottom there is really x to the negative 1. So it's going to become negative x to the negative 2. Just double checking my work here. Yep, everything's all good. So that reason that we do that is now these can cancel out. Boop, boop. We're going to get ln of y equals the limit x approaches infinity of, I'm going to pull that negative 1/2 out in front. So negative 1/2 times 1 over 1 plus 1 over 2x. Yeah, so I'm going to end up getting, if I plug in an infinity here, I'm going to end up getting 1 over 1 plus 0, because remember the x is on the bottom. So 1 over 1 plus 0, so that's a 1. So I'm left with just a, oh yeah, these negatives cancel out too. I was like, I ain't getting a negative answer here. These negatives cancel out. That should be a positive. So, boop, boop, forget about that. Okay, so if I plug that in, the infinity in, I'm going to get a 1/2. So ln of y is equal to 1/2. Again, plugging the infinity here, you're going to get 1 over 1 plus 0, which is 1, times 1/2, which is 1/2. And then we'll raise both sides of the e, so I'm going to get y equals e to the 1/2, which is equal to that right there. There we go. Okay, that is review. Done that a little bit a while ago. All right, so now let's get to this definition part that we had before about ln of x's. So given that ln of a is 2, ln of c is 5, we're going to find these values right here. Okay, so when I take the antiderivative of 1 over t dt, I'm going to get ln of t, absolute value, of course, because we can't have negative values. We're going to evaluate this from 1 to AC. Plug in the AC, you're going to get ln of AC, okay, minus ln of 1. And then ln of 1 is just 0. And then we have the property of the ln's, where this is ln of A plus ln of C. So ln of A is 2. ln of C is 5. We get an answer of 7. We're good to go. Same type of problem here, just a little bit different on the bounds. So take the antiderivative. I'm going to ln of t, evaluate that from 1 to 1 over c. Get ln of 1 over c minus ln of 1. And ln of 1 is going to get 0. So you're going to get ln 1 over c, which is the same thing as ln of 1 minus ln of c. Ln of 1 again is 0. So I'm going to be left with negative 5 because, again, LSE is 5. And that's going to wrap it up for this lesson on logs. Really just diving back in with some stuff from first part of calculus, Calc 1 material type of deal with limits, and jumping in with the integral stuff as well. So this is more or less more of a review lesson.